The first speaker will be Christina Boucher from University of Florida. We've seen Christina yesterday during the panel discussion, and now she will talk about scalable data structures.
Okay, thanks very much. So I want to thank the organizers for hosting this. I think it was a great workshop. So as was mentioned, so today I'm going to talk about scalable data structures, and more specifically some of the challenges and possible advancements that have occurred in the last couple of years. First off, I'm going to apologize. On my plane ride here, I noticed I was getting quite sick, so I hope that I won't interrupt to like sneeze or blow my nose, but right now I have like a really bad cold, so yeah, hopefully I can get through without blowing my nose. Okay, so today I'm going to discuss index-based data structures. To begin, we're going to give a short overview of a couple data structures that many people are already familiar with. Then we're going to present some challenges with their use. And then lastly, we're going to present some more contemporary data structures that have overcome these challenges. And we're going to describe these challenges and advancements in the context of a specific bioinformatics problem. So to begin, what are index-based data structures? The basic setup in using an index-based data structure is to first build an index. Typically in bioinformatics, this is a DNA database. And then use this index to make queries. So that is to search the input for some sort of match. Typically, this is a subsequence match of the database. So this really only makes sense if number one, your input data, your database is quite large, and number two, you have more than one query. So in fact, you have many queries or searches of this database. So most traditional index-based data structures are suffix arrays and Burrows-Wheeler transform, BWT, both of which have been widely applied to short read alignment or read alignment in general, and storing and traversing the De Bruijn graph. So very briefly, we're going to begin our discussion with these two comments. So to begin, we're going to define what a suffix array is. So a suffix array of an input string S is an array of all the suffixes of S sorted in alphabetical order. So here we have an example where we have a small input string shown in green. The first step then is to construct all possible suffixes in their starting index. And then we sort all those indices in alphabetical order, keeping their index around. So the lexicographical ordering of the suffix array implies that all occurrences of all substrings are going to occur together within a range within the suffix array. So what this means is, so in this example, we see that all A's occur together, all C's occur together, and then if we look at even longer subsequences in this small example, AC, then all occurrences of AC are going to occur together within the suffix array. So in order to find any occurrence or all occurrences of a substring, all we need to do is to find the appropriate range within the suffix array. So suffix arrays, in general, are not extremely space efficient. They would require n² space. So the way short read alignment tools like BWA and Bowtie do this is by using the Burrows-Wheeler transform, or BWT. So the BWT is a permutation of the suffix array that takes linear space and allows for fast queries. So informally, we can see it as essentially extracting the last row of the suffix array. And you can go directly from your input text to the BWT array. So the way queries are formed is actually by performing rank operations using the BWT. So rank is an array that is the number of times that a specific character has occurred in the BWT so far. Okay, so here we'll look at an example. So if we focus on the 5th position of at the BWT, we say that an A occurs. So then rank at the 5th position is going to be equal to 2. And that's because A has occurred twice in the BWT until equal to until position 5. So how is BWT and rank specifically used? So using BWT backward search, we can actually find all occurrences of a query string in linear time in the length of the query string. So here we have a small example. We have the string AAC. And how BWT backward search works is you perform a rank operation for each character going from right to left in your query string. And that rank operation is going to set you to a specific range within your suffix array or your BWT array. So in this illustration, we're showing the suffix array, but the same operations can occur and are used with just the BWT array. So at each possible, for each possible character, then we're performing one single rank operation. Okay. And after processing all possible characters within your query string, then the final range that's going to occur within your suffix array or your BWT is going to contain all substrings or all occurrences of that substring within your input text. Okay. So suffix arrays in BWT have been widely applied within bioinformatics. But in some cases, there exist some challenges within their application. So sequence matches where there exist either insertions or deletions or substitution errors are not as easily found using BWT backward search. So first, we're going to look at insertions and deletions. So and the challenge basically comes from how backward search works. So backward search works with the premise that at each possible rank operation, you're going to isolate a specific range within the suffix array or the BWT. Now, if you have to consider an inserted or deleted character, that premise goes away. So you no longer have a contiguous range. So that's challenge number one. So whenever you have insertions and deletions, BWT backward search more or less starts to fail. The second challenge is, and this is kind of two-step challenge, which is mismatches or substitutions. Now, again, if we go back to the backward search, we see that at each possible iteration, we have to essentially search for a specific character. So we're performing a rank operation on a specific character. Now, if your alphabet is small enough, you may be able to perform more than one rank operations with different characters. But if your alphabet is large enough, this becomes impractical. Okay? So more or less, we usually say BWT and BWT backward search is essentially blind. Okay? So you have to perform specific operations about what you're searching for. And for that reason, it can sometimes be impractical in certain contexts. So now we're going to look at a specific example of a bioinformatics problem where we would like to apply BWT in backward search, but it's not quite obvious as to how to apply it and solve the problem. And so the problem that we're looking at is optical map alignment. So many of you may not be familiar with optical maps. So optical map is a ordered genome-wide high-resolution restriction map. So that's a formal definition. Informally, given a particular restriction enzyme that recognizes a restriction site, it's every single location where that restriction site occurred within the DNA. So here we just have like a small token example where we have the restriction site CCGA, and we have the input DNA sequence, and the optical map for that DNA would be 6, 19, and 35. So one of the reasons why optical maps are interesting is that it's much longer than sequence reads. So for example, for the GOAT genome, the average size of optical map is 360,000 base pairs long. So it allows you to get somewhat like genome-wide information. The other sort of important point is that it's now commercially available. So there's a company, BioNano, that's able to perform optical mapping with increasingly high throughput, and it's significantly cheaper now than sequencing. So for this reason, it's been widely used in many different applications. It's now being used within cancer genomics to find structural variants. That's one of the main goals that BioNano is going to be looking at in the next couple of years. So next, I'm going to give you a little bit more insight as to how the process actually works, which is going to take us to our problem. So similar to sequencing, we're going to take several copies of the same DNA, isolate the DNA, fragment it, and then we're going to apply restriction enzymes that are either going to fragment or, in the case of BioNano, nick the DNA. Okay? After this step, a photograph is taken of the elongated and nicked or fragmented DNA. And the photographs are then analyzed in order to both size estimate the nick sites or the cut sites, or the length of the DNA between the nick sites or the cut sites, and then order those values. Okay? So what comes out from this analysis of the photographs is called single molecule maps, or RMaps for short. So after all this RMap data for all the isolated DNA has been accumulated, the next step is then to assemble this RMap data into what we refer to as a genome-wide optical map. And roughly, we would like this genome-wide optical map to essentially contain every position where the restriction site occurs. Now, as you might be able to predict already, one of the key problems then is finding all pairwise alignments between the RMap data. So here's an example. We have two typical RMaps, and we can see that these numbers are in KBP. And what we want to do is we want to find a suitable alignment. Okay? So ultimately, we would like the alignments, we would like the alignments to be based on finding matched pairs of conserved restriction sites. So this is sort of illustrated by the nearly vertical lines matching the fragments of one of the RMaps to the fragments of the other. Now, several challenges actually exist. So in order to find such an alignment, we must be able to tolerate missing cut sites. Okay? Now, due to error within the optical mapping system, there's often like incomplete digestion or missed nick sites. And those are going to show up as a cut site that should have been there but isn't in the data. So similarly, there may also be false cut sites, and this is just due to the fragile nature of the DNA. Okay? So this is like an inserted cut site. The last one, which you may already be able to predict, which is there's going to exist a significant amount of sizing error. Okay? So sizing error is just the fact that we're essentially approximating by looking at these photographs what the length of the DNA is. But trying to estimate that exactly is unlikely to occur. So here in this particular case, we have 3.9 kbp, and we have to match that to 4.2 kbp. So previous approaches to our map alignment use dynamic programming. Okay? So one of the challenges with that is that they don't scale well to larger genomes. Alternatively, we would want to use an index-based data structure, i.e. BWT, to improve the time efficiency. In order to do that, as we go back to our discussion of index-based data structures, we would first need to build an index of all the concatenated RMAPs. And then we would need to search that index for our query string. So in this particular case, the query string is just going to be a single RMAP. Now, the challenges in the first step is that we have these false or missing cut sites. And they're kind of akin to insertions or deletions that occur within sequence data. The second one is we have sizing error. And this is problematic because, again, we no longer can search for an exact match. So next, we're going to go over our solution to the first challenge. And the solution for our first challenge is to use something called the generalized compressed suffix array, or in short, GCSA. So the main insight about GCSA is to notice that given an input string, we can essentially use it. We can think about that as a graph. So a directed graph where there exists a character, a node for each possible character, and then there's going to be a single path from the start character to the end character for each string. So the generalized compressed suffix array, or the GCSA, allows this view to be extended to more complex graphs. So now we're going to have a single path for each possible alternative spelling of that input string. So we're going to look at a more complex example here, which is going to illustrate this point. So here we have a multiple alignment of 4 DNA strings. We're going to focus on one specific region of that, and we're going to look at the string that is relatively common to each one of these input strings. So, and I think Ben sort of illustrated this example so far. But so for that particular consensus string, we're going to build a single path that is going to spell out that string. And then we're going to consider all possible alternatives that are illustrated within the multiple alignment. So every single one of the alternatives is going to correspond to a path within this graph. So given this directed acyclic graph, or this automaton, then the GCSA will, in order to apply the suffix array, we need to efficiently store all the vertices in the edges in a manner such that the BWT properties still hold, meaning that all paths with the same subpath fall within a contiguous range within the BWT. So in order to do that, we're going to take our directed acyclic graph, or our automaton, and we're going to turn it into something that we refer to as a prefix sorted automaton. Okay? So the first definition that we're going to look at is a vertex V. So a vertex V is prefix sorted by its prefix P of V if all labels of all paths from V, which is the current vertex, to the last vertex, share the common prefix P of V, and no other path from any other vertex in the graph U to the final vertex also has that same prefix. Okay? So that's our definition of a vertex V being prefix sorted. An automaton A is prefix sorted if every vertex within the automaton is also prefix sorted. So a non-prefix sorted automaton can be made prefix sorted by the addition of, or the process of duplicating vertices and incoming edges until we remove all ambiguity within the paths of the graph. So here we're going to look at an example. So here was our automaton that is non-prefix sorted. And we're going to focus on this particular node A. And we can see that we have the following prefixes, or the following sequences that can occur going from A to our final node. So if we look at this, we can see that it is non-prefix sorted. So there's no common prefix such that node, to make that particular node prefix sorted. So in order to make it prefix sorted, we're going to essentially make 3 duplicates of that node. And those 3 duplicates occur because there exist 3 outgoing edges. So for every single outgoing edge, we're going to duplicate, we're going to create a unique path. And that's going to represent all possible unique strings or prefixes that can go from that current vertex to the final vertex in the automaton. So after creating the prefix sorted automaton, then we can store all the edges in the BWT. So how we do that is that we look at all possible prefixes and their incoming edge. So if we look at one particular example here, we see that we have ACGT that occurs, and that's going to be our vertex that we made a duplicate of. And we can see that the incoming edge to ACGT is going to be equal to T. Okay? So what we do is we take all possible prefixes, then we're going to colexigraphically sort them. And finally, then we're going to use this bit vector M to store all incoming or outgoing edges. Okay. So what we actually do is we actually store the automaton simply by using the BWT array and the M bit vector. So next, we're going to return to our RMAP application. So how we accomplish this is for each possible RMAP, we're going to create a single path in our automaton. And then we're going to consider all possible alternatives. So when we mean an alternative, we mean that assuming that the cut site that we have is going to be a false cut site. Okay? So if it's a false cut site, what we have to do is we have to account for that by creating a new edge and taking the sum of the neighboring fragments. So in this particular case, we're going to assume that the following is a cut site. The sum of the neighboring fragments is going to be equal to 7. And then we're going to create this alternative path. So we're going to do this not just for this single cut site, but we're going to do this for all possible cut sites. Okay? So after creating the automaton, then we simply need to make it a prefix sorted automaton and then store the automaton using the generalized compressed suffix array. So what this is going to allow us to do is we can now perform queries simply using our final data structure here, which is BWT and M and F. So M and F are just bit vectors that help store the incoming and outgoing edges. So that's challenge number 1. Challenge number 2 is the fact that we have this sizing error. So in order to overcome this sizing error, we're going to use something called wavelet tree. So why is sizing error a problem? Well, again, so at each possible position within our query string, we're going to have to perform a rank operation. Now, we could look at alternatives if we had a small alphabet. But in this particular case, our alphabet is huge. So the number of unique fragment sizes for the goat genome was over 16,000. Okay, so with an alphabet of size over 16,000, it then becomes impractical to look at alternatives by performing various rank operations at each possible recursion of the backward search. Okay, so we can't perform 16,000 rank operations. So what we do is we construct something called the wavelet tree when we construct our generalized compressed suffix array. So a wavelet tree converts a string into a balanced binary search string, a balanced binary tree of bit vectors where 0 replaces the first half of the symbols, 1 replaces the second half of this symbols, and this definition is then applied recursively until there exists no ambiguity. Okay? So here we're going to look at an example. So here we're going to go back to the DNA alphabet just to exemplify what a wavelet tree is. Given the following input string at the first level of the wavelet tree, we're going to encode ACGT as 0011. Okay? Then we see that there exists ambiguity. Okay? So at the second level of the tree, in order to break ambiguity, we're going to encode AC as 01 and encode GT as 01. Okay? So what the wavelet tree allows us to do is then to perform queries such as which positions or which symbols in AG exist within our input string. Okay, so which positions have a character that's A, C, G, or T. A, C, or G. So thus, it's going to allow us to essentially perform range operations or range queries. So we can use this now in our modification of our backwards search. So here, given a particular number x, we want to find all matches of x that fall within the range x plus or minus y, where y is some sort of threshold for our tolerance value. Okay, so the range in the error that we're going to expect. So we're going to illustrate this using an example. So here would be, you know, a typical optical map. And here, what we want to do is we want to match 9, but we're going to allow for a certain amount of errors. So our tolerance value is going to be 3 in this particular case. So then we're going to, I'll wrap up. So what this allows us to do is it allows us to find all positions that where there exists a symbol within the range 6 and 12 within our input string. So this is going to be a modification of our backward search. So at each possible position or each possible iteration of backward search, instead of performing a rank operation using the rank array, we're now going to perform a rank operation using our wavelet tree. Just to wrap up, there's still a lot of challenges that exist within this spectrum. So right now, we can only do acyclic graphs. That's kind of the barrier within BWT. We have no way of actually compressing and searching and creating indexes for cyclic graphs. Possible applications include alignment of PacBio reads. And there does exist one of the key challenges, which I think was brought up when Ben gave his talk, is in order to make this practical, the GCSA, is you can't consider all possible variations. So you have to have some sort of way of pruning the possible variations. And then remaining challenges people are looking at is sort of deeper, better compression of the BWT index. Okay. So
maybe we do a quick question. Okay, we can always discuss offline. Let's thanks Christina again.
Okay.